Welcome to this video to finish out chapter number 2. So let's work a couple of Henderson-Hasselbalch type calculations. So here we go. An unknown amine is 80% deprotonated at pH 10.1. What is the pKa of the amine? Well, here's what I would do. I would say, okay, what information has he given me? Well, it's an unknown amine. So let's just write the general formula for an amine. It doesn't really matter. I'm just going to choose a primary amine for no particular reason. I know we have this equilibrium set up in terms of the acid and base forms of this particular amine. This is the base form. This is the acid form. And so the problem gives us 80% deprotonated at a particular pH value. Well, that means 80% is in the base form, 20% is in the acid form. I want to know what's the pKa of the amine. Now, you know how this works. I talked about this the other day. I'm really looking for the pKa of the acid form. That's what I'm looking for. So to do this is a fairly straightforward Henderson-Hasselbalch type calculation. Let's just do a little bit of math here, or algebra, I guess. Log of B over A, base over acid. I want to solve for the pKa, so we can just go ahead and do a little rearrangement. pKa is pH minus the log of the base over the acid. And now I can put in some values here. So pKa equals the pH. Hey, I was given that, 10.1 minus the base 10 log of the base over the acid. Well, we have to come up with an appropriate ratio. We don't have the concentration of the base. We don't have the concentration of the acid. But if we know their relative ratios, we can solve this problem. So think about having 100 molecules. This makes it easy. You got 100 molecules. Of the 100, you have 100 molecules of this amine in water. How many of them are in the base form? 80. How many are in the acid form? 20. There you go. So we've got 10.1 minus the base 10 log of 80 divided by 20. And again, this is just kind of landing the plane here. 10 minus 1 minus 0.6 equals a pKa of 9.5. Now, did we know that we should have had a particular answer even before we started? Well, the problem, even before we started, maybe I should have done this before we started, you knew, since it was in 80% in the base form, you knew that the pH had to be greater than the pKa. You knew that to begin with. That's the only way you're going to have a greater amount in the base form. So you didn't know the exact number, obviously, but you knew that the pH 10.1 had to be greater than the pKa value you calculated, and that turned out to be true here. The pKa of this amine is 9.5, and of course that pKa is for the acid form, or the conjugate acid form, however you want to say it, of the amine. Okay, well, this is just one way to do this is just one example of these types of calculations. Before I forget to tell you, there's some extra problems on Canvas. It's like HH help, I think, Henderson-Hasselbalch help. These are not difficult. We're not pushing back the bounds of higher mathematics here, but you've got to be able to know the scenario that you've been given, and you need to understand the information I'm wanting you to derive. And so sometimes, if you're not paying attention, that gets you kind of tripped up. So let's go ahead and do another one example to kind of finish out this chapter. At pH 5.1, what percentage of acetic acid molecules, pKa of 4.8, will be in the ionized form? Well, that is the problem. And let me, yeah, this makes me happy here. Hang on a second. Let me do a little bookkeeping. Aha, I like that. So in this case, is it important to know what type of molecule that we have? Is it important to know that we have a carboxylic acid? Well, it is important because I'm asking you about the ionized form. So, both forms of acetic acid are not charged, are not ionized. So you need to know which form of a carboxylic acid is ionized. Okay? So this is where I think you really do have to draw out acetic acid, or just some general carboxylic acid if you don't know what acetic acid is. Although we use it over and over again, you probably should know what that is. That's the equilibrium we're working with. We're in water. I'm not showing you water in the equilibrium, but we could do that if you really wanted to. It doesn't matter really. This is the acid form. This is the base form. And then I'm giving you, or I'm asking you, what percentage of the molecules are in the ionized form? Well, for acetic acid, this is the ionized form. So I'm really asking you what percentage of acetic acid molecules that are placed in water and the pH adjusted to 5.1, what percentage of them are in the base form? Now, before we even get started, can you give me a ballpark? Can you give me some information to kind of do a quality check on our answer? So we know already that the given information that the pH is greater than the pKa of acetic acid. I just gave you that. That's in the problem, right? So you know that the major form is the base form. So you know the answer should be greater than 50%. You know that already. I think it's a good idea to do that before you even get started. Okay? Well, here we go. And let's see what we get. Hopefully it's greater than 50%, or we're going to have to rethink some things. So let's just start out with our equation. And we really need to calculate we need the ratio of B over A is what we're going to have to get. Can we get that ratio? Can we get the percentage of the molecules in the base form and the percentage of molecules in the acid form? Well, sure we can. So here we go. pH minus pKa equals the base 10 log of B over A. And then, again, we're not pushing back the bounds of math here, but here we go. 10 raised to the, now this is important, pH minus pKa in parentheses equals B over A. All right, there we go. Now we've got this information, so 10 to the 5.1 minus 4.8 equals the ratio of B over A. All we did here was just take the anti-log of both sides. And of course, if you take the anti-base 10, if you take the anti-log of the log, then it just goes away. So let's go back up here. It looks like we've got 10 to raised to the 0.3 equals B over A. If you take 10 and raised to the 0.3, this is going to be 2 equals B over A. Now, this is where some people, if you haven't done this before or haven't done it in a while or not thinking about it, this is where people go off the rails a little bit here. Really, I'm telling you that there's 2 molecules of B for every 1 molecule of A, right? That's really what I'm telling you. So what is the percentage of B? Well, I need to pick a sample size. Okay, what I do is sometimes these ratio, it may not be whole number, so I just add the top number and the bottom number. So I'm going to say the sample size is 3. Okay, so out of 3 molecules, 2 of them are B, 1 of them are A. That's what I know to be true. So basically the percent B is 2 divided by 3 times 100% equals 66.6, and we'll just stop there, percent. And the rest will be percent A. But I wanted percent B. So what percentage of the molecules will be ionized of acetic acid? Well, 66.6% of acetic acid molecules in water at pH 5.1 will be in the base form and be negatively charged. We knew it was going to be over 50, so I feel good about this. Let's just give ourselves a smiley face there. And so I've done 2 examples for you of the Henderson-Hasselbalch equation. There's many different ways this can be done, and I've given you some extra practice on Canvas. Sometimes we want to be quantitative about different ionization forms. Sometimes we just want to be qualitative, like the base form is the major. And sometimes we need to know, oh, the base form is 66.6% of the molecules. So the Henderson-Hasselbalch is quantitative, whereas just comparing pH and pKa is qualitative. All right, that's it. Chapter 2, boom, in the books. And then you're going to figure this out. We're going to start Chapter 3 on Friday before Labor Day. All right, thanks.